You've probably heard about the Lambda-CDM model, right? It's the heavyweight champ of cosmic explanations, banking on the elusive dark matter and dark energy to describe why our universe is expanding at an accelerating rate. But what if I told you there's a new contender in town? Enter the revolutionary proposal by a scientist named Kumar. He suggests that maybe, just maybe, we don't need dark energy or modified gravity to explain cosmic acceleration. His idea? Our universe might be just one half of a cosmic duo, paired with an anti-universe that was born alongside us at the Big Bang. Now hold on to your hats, because here's where it gets wild. In this anti-universe, time flows backward. Yes, you heard that right, backward. This isn't science fiction, it's a serious suggestion based on quantum theory, which comfortably allows for such pairings. But how does this solve the puzzle of cosmic expansion? Kumar's model points out that such a universe pair would naturally exhibit accelerated expansion, respecting what's known as the null energy condition, all without the need for dark energy. It's like finding out you can run a marathon because you actually have an invisible twin who shares the load. And there's more. This model isn't just a wild guess. It draws parallels with Stephen Hawking's area theorem. It deals with causal horizons and suggests that the Big Bang itself might be the causal boundary linking our universe with its mysterious twin. So, what do you think? Is the anti-universe model the key to demystifying the cosmic acceleration? Could we, in our quest to understand our own universe, discover an entire mirror world where time runs in reverse? It's concepts like these that keep the passion for cosmic exploration alive, pushing the boundaries of what we understand about our spectacular universe. But how can we actually test or verify such a mind-bending hypothesis? Testing the hypothesis of an anti-universe requires innovative approaches, as it deals with concepts that are not directly observable with current technology. Let's explore some potential methods that scientists could use to verify this hypothesis. First up, gravitational waves. Future experiments designed to detect gravitational waves could provide valuable insights. Gravitational waves are ripples in space-time caused by massive objects and events, like black hole mergers. If the anti-universe model is correct, it might leave a unique signature in the gravitational wave background. Next, neutrino mass. Pinning down the mass of neutrinos could also be key. Neutrinos are subatomic particles that are incredibly difficult to detect due to their weak interaction with matter. The anti-universe hypothesis suggests that dark matter could be a new flavor of neutrino. Measuring the mass of neutrinos could help confirm or refute this aspect of the theory. Then we have CPT symmetry. The combined symmetry of charge, C, parity, P, and time, T, is a fundamental principle in physics. If every interaction observed in nature respects CPT symmetry when charges are flipped, mirror images are taken, and interactions are run backward in time, this could support the idea of an anti-universe existing in tandem with our own. Another method involves the cosmic microwave background, or CMB. Observations of the CMB, which is the afterglow of the Big Bang, could reveal patterns or anomalies that align with the predictions of the anti-universe model. The CMB is a snapshot of the early universe and carries information about its structure and composition. Finally, quantum fluctuations. Quantum theory allows for the creation of particle pairs that pop in and out of existence. If the universe and anti-universe were created as a pair, there might be quantum fluctuations that could be detected indirectly through their effects on the observable universe. Each of these methods represents a fascinating frontier in our quest to understand the cosmos. While the anti-universe hypothesis is still in its early stages, the journey to test it promises to be as thrilling as the concept itself. Let's take a closer look at one of the most mysterious particles in the universe, neutrinos. These elusive particles could hold the key to unlocking the secrets of the anti-universe. Neutrinos are elusive particles that interact with matter through the weak nuclear force, one of the four fundamental forces in nature. So how do neutrinos interact with matter? Let's dive in. First, we have weak interactions. Neutrinos primarily engage in two types of weak interactions: charged current and neutral current interactions. Charged current interactions occur when a neutrino converts into its corresponding charged lepton, like an electron muon or tau, upon interacting with a nucleon, which is either a proton or neutron. This process involves the exchange of a W circumflex plus or W circumflex boson. For example, an electron neutrino can interact with a neutron to produce a proton and an electron. Next, we have neutral current interactions. In these interactions, the neutrino remains a neutrino, but transfers momentum and energy to the struck object, such as an electron or atomic nucleus. This interaction involves the exchange of a Z circumflex zero boson and does not change the type of neutrino. But there's more. Quantum mechanics tells us that neutrinos are quantum objects and their interactions are probabilistic. They can pass through matter without interacting due to their tiny mass and neutral charge, making them extremely difficult to detect. One of the most intriguing aspects of neutrinos is flavor oscillation. Neutrinos exist in three flavors: electron, muon, and tau neutrinos, and can oscillate between these flavors as they travel through space. This oscillation can also occur when neutrinos pass through matter, a phenomenon known as the Mikheyev-Smirnov-Wolfenstein (MSW) effect. Finally, let's talk about detection. Neutrino detectors often use large volumes of water or ice to increase the chances of neutrino interactions. When a neutrino interacts with the medium, it can produce a charged lepton, which then emits Cherenkov radiation that can be detected. The enigma of neutrinos not only challenges our understanding of the universe, but also offers a tantalizing glimpse into the possible existence of an anti-universe. As we delve deeper into the mysteries of these ghost particles, we move closer to unraveling the cosmic puzzle that surrounds us. We've journeyed through the enigmatic hypothesis of an anti-universe and explored the elusive neutrinos, often dubbed as ghost particles. But what truly makes these particles earn such a spectral nickname? First, we have the weak interaction. Neutrinos barely interact with other particles due to their weak force interactions. Imagine a particle so elusive it can pass through entire planets without being stopped or even slowed down. This ghostly ability is one of the defining characteristics of neutrinos. Next, consider their lack of electric charge. Unlike other particles, neutrinos have no electric charge, which means they don't get deflected by magnetic fields. They travel in straight lines across the vast expanses of space, undeterred and unseen like cosmic phantoms. Then, there's their tiny mass. Neutrinos have an incredibly small mass, making them almost impossible to detect as they don't significantly affect the matter they pass through. This tiny mass adds to their ghost-like nature, allowing them to slip through the universe unnoticed. Despite their elusive behavior, neutrinos have a pervasive presence. They're one of the most abundant particles in the universe, created in processes like nuclear reactions in stars, during supernovae, and in the aftermath of the Big Bang. Their omnipresence in the cosmos makes them a silent witness to the universe's grand events. But perhaps the most haunting aspect of neutrinos is the challenge of detection. Detecting neutrinos requires highly sensitive and specialized equipment, as they rarely leave a trace. This adds to their mysterious ghost-like reputation, making them one of the most challenging particles to study. Neutrinos are not just ghostly, they are cosmic storytellers, carrying with them secrets of the universe's origins and evolution. As we continue to develop advanced detection methods, we inch closer to unraveling the mysteries these ghost particles hold.